I'll start with a quick review for this book or course, The Science of Energy. I'll give this book 4 out of 5. I almost give it a 5. I think it's a great course. I learned a lot out of it. It has a lot of physics, so if you really dislike physics, it's not maybe the best for you, but I think it's a very interesting and important book, especially right now. We have climate change, etc. So it's a really good book or course to go through what's going on. He's a great professor. I would say maybe it's one of the reasons that I haven't gave it a good 5 stars is because there is too much math, which is doesn't transform so well. You can just don't have to do all of it. It's not that it was hard. It's just kind of hard to, especially if you're listening to it, it's kind of hard to follow along. But overall, he's a great professor, straightforward, easy to understand, easy to follow. Great lectures. So I would definitely recommend. Let's see the notes. Energy prices affect us in every little part of life. Everything we buy, even food, is affected by energy prices. In many little things, our house, our rent, everything is impacted in some way by energy prices. 1 joule is lifting 1/10 of a kilogram a meter. That's a joule. It goes through joules a lot. I don't know why they use it so much. It's a little bit of confusing because we're not used to use joules. But what joule is lifting 1/10 of a kilogram. So 0.1 a meter. That's a joule. And then a watt. 1 watt is lifting that for a second. Each second is a watt. Coal contains energy which released by heat. So this is where it contains. It's literally fossil fuels in a way. And the way to release that energy is by heat. Energy stays constant. Oftentimes kinetic energy would transform to heat. There is no energy doesn't lose. It's one of the rules. But oftentimes kinetic energy, because we move, would transform into heat. So there is some energy lost. Energy lost to friction is transforming to heat. That's the friction. Friction causes heat in a way. Heat is atoms who are excited and move more. That's what heat is. It's just moving more rapidly. Heat can move energy through radiation, convection, which is buoyancy, and conduction. That's the 3 ways energy moves. Radiation, like sunlight, for example, microwave radiation. Convection, which is like moving other things around, and conduction, which is like things touching each other and they warm themselves, or energy other ways. When the oven is glowing, that means we are now able to see the heat as a visible radiation. What's the difference is that we're not seeing that now it's become visible. The radiation basically is now visible. It wasn't visible before. Now it is, because the higher heat. Lower heat, where there is still radiation, but we're not seeing it. Hot moves to cold, not the other way around. It's not cold moves to hot, hot moves to cold. It's one of the rules. Most energy production is lost to heat. Only about a third is used. Most of it is lost. I think there is, depends what, but most production is only about a third, which is amazingly inefficient in a way. Compressing and expanding gases affect heat. So compressing is making it colder, I think, and decompressing, or the opposite. Decompressing is making it colder, and compressing it makes it hotter. It's the same, one of the ways that air conditioning works. More coils create higher voltage, which is how transformers function. There's more coils, there's higher voltage, and transformers is how they transform voltages, because coming out of the plant is higher, very high voltages than what we use in the house, for example. Photosynthesis is not efficient. We also need to expand that forward. Only a few percentages is used. Green light, for example, is not absorbed. So photosynthesis is very not efficient. It's a very few percentages actually being used by plants. For example, green light is not absorbed at all. That's why we are seeing it in a way. Coal is the most efficient source of energy per unit. So it's a very compacted energy form. Coal is the energy equivalent of junk food for the same reason, because it's very compact, but it also creates a lot of toxins and it doesn't burn well. And so it's very compact, very energy, full of energy, but it's not good. Mining is often releasing toxin into the air. So mining does. Many times we cause a problem by it. Now there is two parts of this. Let's go to the second part. I don't know why they started doing it. It's kind of annoying. All right. Solar energy strip electrons, which allows them to move as part of the current. That's what solar does. Solar energy does. They strip the electrons and then they go into the current. Wind is created by the sun as it warms some places more than others. That's the main contributors to wind is sun. Warms one parts up, and as we learned, we have hot moves to cold, and then there is a wind. Wind is also affected by the Earth's rotation. It also causes some rain patterns. Rain is eroding the land. If not for volcanoes and tectonic shifts, there would be no land left, because it's eroding the land, rocks, and other forms of land. And as he said, if there's no volcanoes, which creates more land, more rocks, and tectonic shifts, which raise everything up, but that's how mostly mountains forms, and there would be no land left. Interesting. Biofuels often use fermentation to create the fuel, as bacteria releases toxins. That's what they do in biofuels, and how, in a way, alcohol is a biofuel. Human energy consumption is about 18 terawatt hours. That's the total human consumption at the moment. I started to look into it. It's not, I don't know where was it on, but it's kind of different right now, but it's a lot. 1 hour of sunlight energy is more than all humans use in a year. And he did a calculation, which was one of the hard things that was to follow, but you don't have to follow, just look to see that it works. But 1 hour of sunlight is what humans use the whole year, and he said it's about right. One form of energy storage is sending water upward when surplus exists, and using hydropower when needed. So we have surplus of energy, you send the water upstream, and then using just a hydropower plant, regular ones, just water flows back down, and you get the energy back. Compression and decompression of air, and using gravity in various forms are more ways to store energy. Similar idea, doing work when you have surplus, and then using that work when we need it, when there is less energy. For example, sunlight or wind, one of those renewables. Average household energy use is around 2.5 kilowatt hour over a year. That's average. That's a household. 1.25. Transportation by boat is the most efficient, while by air is the least. Air is not efficient, boat is. Bicycling is more efficient than walking in terms of energy spent. That was amazing to know that we actually spend a lot of energy walking even. I think he says like it depends how fast you're driving, how fast you walk, and things like that. I forgot. I should have maybe take a note on that. But a car is only in a very specific way is more efficient in walking, for example, or running. Maybe I forgot which one is it. You can look into it if you're interested. But bicycling is better than walking. Interesting. And we have the last one is in the US, every person uses about 10 kilowatt hours. Which is like, I'm not sure it's for a day hours because it's like weird, especially when I wrote down up a little bit up here that it's about 1.25. So that's kind of make it a little confusing. Maybe it's hours, so it has to be per hour. I'm not sure. Maybe it's in the US and that's in the world. I'm not sure how it. I should look into it. But that's all for this. And again, it's a 4 out of 5. Definitely recommend. It's a good course or book. Thank you.